What's up? Welcome to another episode of How to Geometry, where I go through the basic concepts of geometry. In this particular video, we are going to look at an introduction to polygons. Very basic. There's four main formulas that you're going to need to know to be successful in this particular topic, and I'll go over them, show you a couple examples. So without further ado, let's get it. Okay, so let's just start by getting some terminology out of the way. What is a polygon? Right, it's a closed figure, meaning all the sides are connecting, and it's line segments that from connect endpoint to endpoint. So a closed figure with straight lines. That's basically what a polygon is. There's two types of polygons, right? There's convex and concave. Now, I wouldn't get too hung up on the formal definitions of convex and concave. I think it's more obvious when you see pictures. But so a convex polygon is basically when the diagonals are not on the exterior of the polygon. And concave is when you have a diagonal that is on the exterior or outside of the polygon. So you'll see this in a second as far as a diagram is concerned. So we'll look at what is a polygon and what's not a polygon, right? By classification. So we see a couple of examples. The first example, immediately, it has a curve, right? It has a couple of curves. Just one is all you need. So not a polygon. Second example, so it's closed, right? Everything's connecting, and they're all straight lines and a diagonal. So let's consider diagonals. So from vertex to vertex. All right, here's a diagonal. There's multiple diagonals. Right. Here's a diagonal. These are all still on the interior. However, because there's just one diagonal that is outside, we consider this concave, right? This is a concaved polygon. Now, if you think about it, the root of the word, right? Cave, like the sides are caved in. That's one way to think about it. But really, if you have a diagonal that is outside, when you connect the vertices, then it's a concaved polygon. The third example, this moon crescent looking shape, it has this curve, so definitely not a polygon. The hexagon, six-sided shape, it's definitely a polygon. So is it convex or concave? That's the question. Well, if you make a diagonal, no matter how you make the diagonal, because it's inside, right? All the diagonals are inside. This is convex. Convex. And then last, by definition, right, a closed figure. So this is definitely the opposite of closed, right? This is not connected. So this is open, or not closed, rather. So not a polygon. So the classes are pretty easy, or classifications are pretty easy. They also go by a number of sides. So n is the variable that's reserved for sides. So when you hear n sides, or how many sides a polygon has, n will be the variable of choosing. And that's just standard across the board. That's not something I made up. Okay, the three types of polygons. Technically, there's, I guess, four, but the three that we're looking at, equilateral, equiangular, and regular. So equilateral, all sides are equal. And equiangular, all angles are equal. And if it's regular, a regular polygon is both equilateral and equiangular at the same time. And equiangular. There's I guess a fourth classification of neither or irregular. Irregular. So a polygon, that's a polygon, but all sides are different and all angles are different. That would be an irregular polygon. So let's see a couple of examples. So first off, we have a equilateral triangle. So this is for sure. These tick marks imply that the sides are equal. So equilateral. And then these arc marks imply that the angles are all the same. So all angles are equal, all sides are equal. This is definitely a regular polygon. Second shape, quadrilateral. Here the tick marks imply that the sides are all the same, but there's no arc marks on the angles. The angles are definitely different. So this is equilateral. Okay, the third shape we have, what do you think? Tick marks imply that these two are equal, but then the double tick marks imply that they're equal. So all the sides are different, or at least all the sides are not equal. And there's no arc marks, so the angles are all going to be assumed to be different. So this is neither. It's irregular, one might say. Okay, gotta forgive the accuracy of this drawing, but the boxes in the corner imply that it's a right angle, 90 degrees. So it has all four angles that are equal to each other, right? 90. So this would be equiangular. A circle is not a polygon, right? It has a curve. So this is not a polygon. Right? By definition, it has to be closed and have straight lines. Now, I get it. It has infinitely many straight lines, but by definition, this is not a polygon. And last but not least, tick marks imply that the sides are equal. Boxes imply that the angles are equal. So this will be a regular polygon, right? AKA a square. Okay, let's look at some more little details. So a diagonal of a polygon is a segment that connects two non-consecutive vertices. So non-consecutive meaning not in a row. So a triangle has three vertices, and there isn't any diagonals in a triangle, right? If you connect the vertices, these are sides. So there's no diagonals. So three sides has zero diagonals. Quadrilateral, if you just do one vertice, right? Or not one vertice, vertex to vertex, non-consecutive. So we have one, two diagonals. So here a four-sided shape has two diagonals. Pentagon, five-sided shape. We have a couple. We have 2, 3, 4, 5. So a five-sided shape has 5 diagonals. Kind of see where this is going. So every vertice has to connect to every non-consecutive vertice, right? Because if you do a consecutive vertice, then that would just be a side. So here, it's easy to get confused in this. So 1, 2, 3. So those are diagonals, supposed to be straight, not curved. 1 or 4, 5, 6, and then we'll go. So some of these will repeat, right? 6. This would be 7, 8, 9. So a 6-sided shape has 9. And you can tell because each vertex has three. Three, 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 three. Okay. All right, the next one gets very interesting. So an 8-sided shape. So each vertex is going to have 1, 2, 3, 4, 5. And again, some of these will be counted twice. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I missed one. 20. So an 8-sided shape has 20 diagonals. There's a formula to figure out, right? Because if we wanted a higher sided polygon, it's going to take forever to try to draw these out. There's a nice formula. The n minus 3 divided by 2. I guess you could pause and try to figure out that pattern, but that's what it is, right? It's n times n minus 3 divided by 2. Another neat property is that if you connect just from one vertex, right, not all the diagonals, but just from one vertex, and you split the polygon into triangles, you get a very interesting property. So, for instance, in the far left shape, it's already a triangle. So we're relating the sides to the number of triangles. So 3 sides makes 1 triangle. Quadrilateral, if you have from vertex to vertex, so you have a 4-sided shape, it can make 2 triangles, right? 1, 2. So if you think like, why is this important? Because in a triangle, we know that the degrees add up to 180. And the idea is that in a 4-sided shape, because I can split it into 2 triangles, this would be 180 plus 180 degrees. So technically 360. So a 4-sided shape will add up to 360 degrees. In a 5-sided shape, you can make 2 diagonals, and this will make 1, 2, 3 triangles. Again, each triangle is 180 degrees. So 180 times 3, we're going to get 540 degrees total, which this will come up in a moment. A hexagon, a 6-sided shape, can be split into, well, it's supposed to be from vertex to vertex. That was bad. Into 4 triangles. And an octagon, 8-sided shape, can be split into 1, 2, 3, 4, 5, 6. So if you look at the pattern relating the sides to the number of triangles, the triangles are always 2 less than the number of sides, right? And sides being n. So n minus 2. N minus 2. That is the pattern, I guess, for the number of triangles in a polygon. Okay, and this leads into a couple of theorems. So I wouldn't get too hung up on like the wording and the formality of the theorems, right? Again, knowing it is one thing and knowing how to apply it is better. So the sum of the interior angles in a convex polygon with n sides, right? It doesn't matter what the sides are. will be n minus 2 times 180. So this means you add up all the angles in whatever side polygon you have, and it's the number of triangles n minus 2 times 180, right? And that would be the total degrees for whatever polygon you have. So n minus 2 times 180, that is the most important formula actually at the moment. So n minus 2 times 180. Again, sum of the interior. Now, if I want to know what each angle is, you have to take the total number and divide it by the total number of sides. So each interior angle of a regular polygon with n sides is n minus 2 times 180 divided by n. So this is the second one. So you don't necessarily have to remember another formula. Just know that you take the first formula and you divide it by the number of sides. That'll tell you what each interior angle measures. All right. A nice theorem is that the exterior angles, meaning if I were to extend each of these angles out, or each of these sides out, I would create an exterior angle that is outside of the polygon. Right here are all the exterior angles. And a neat property is that when you add up all these angles, regardless of the number of sides, it's always going to be 360. It's the beauty of it. Right? It's always going to be 360. 360 degrees. So exterior angle, the sum is always 360. It's going to play a role later, but using this number, using this fact, will make some of the calculations easy. So just remember that an exterior angle, right, it's whatever that interior angle is minus 180, right, subtracted from 180. Because a straight line is 180. So that would be the exterior, right, outside. All right, and if I want to know what each exterior angle measure is, then that would be 360 divided by the number of sides. So 360 divided by the number of sides. And that's really it. So these are the four big ones. So now, given any side, I just run this number through my formulas and I can figure this out. So if n is equal to 16 and I want to know in a 16-sided regular polygon, these four ideas, sum of the interior. So if I add up all of them, I can do 16 minus 2 times 180. It'll come out to 2,520 degrees. And if I want to know what each measure of the interior is, I take that number and I just divide it by the number of sides. 157.5 degrees. Okay, the sum of the exterior, right? You add up all the exterior angles. And this one's the easy one because it's always the same number every time, 360. But if I want to know what each exterior angle measures, I take 360 and I divide it by 16, which would be 22.5 degrees. Okay, so let's see a couple more examples. So in the previous example, we were given a side, or we were given the number of sides, and we want to find the various degrees. Well, now we're given a specific degree, and we need to figure out how many sides the angle came from. So if we're given the measure of each exterior angle, So exterior angle, each exterior angle. So the formula associated with this is 360 divided by n. All right, they're telling us that this is 20. So it's going to be equal to 20 degrees. And we need to figure out how many number of sides it has. When the variable's in the bottom, there's a nice property. So, I mean, algebraically, you can multiply both sides by n, divide both sides by 20. But algebraically, like there's a nice little shortcut. When you see that there's a variable in the bottom, you can just switch these two. So you're going to get n is equal to 360 divided by 20. So only when the variable is in the denominator do we have this nice little switch. There's nothing wrong with multiplying both sides by n, canceling on the left, dividing both sides by 20, canceling on the right, and you get n is equal to 360 divided by 20. Like, it's the same thing. So when you put this in the calculator, n is equal to 18. Okay, let's look at the next one. So we're given the measure of each interior angle. If we look, each interior is n minus 2 times 180 divided by n. So n minus 2 times 180 divided by n. So this is what they give us, right? 168 is equal to this. Okay. Now, there's nothing wrong, again, algebraically solving this thing. Multiplying both sides by n, distributing the 180, and then combining like terms, right? We've all gone through Algebra 1, so we know how to do this. However, if we think outside the box for a moment, there is a way to make life easier. Because I don't know how many sides this polygon has. I do know that it's a regular polygon. So I know that at some point, it's going to have a side. Actually, it's going to have two sides that make some sort of corner, some sort of vertex. And it measures 168. Right, and however many sides it has, that's how many vertices it's going to have that measure 168. Okay, let's use the fact that the sum of the exteriors must equal 360. So what am I saying? I'm saying that if we extend this line out, we now create an exterior angle. And however many of these angles, it must add up to 360. So we know that a straight line is 180. So 168, or 180 minus 168 will give us 12. So I know that the exterior angle is 12, right? Logically, it has to. So what that means is that we're right back at the last example. When they said that each exterior angle is 20, we have a nice little formula, and we can do n is equal to 360 divided by 20. That's what we did. So now it's the exact same problem except with 12, because 12 is the exterior. We have a nice formula that says the number of sides is equal to 360 divided by the exterior angle, which is 12. So 360 divided by 12 will give us 30. So this is a 30-sided polygon, and each angle will measure 168 degrees. So you can see how every time you have an interior angle, each interior angle, not the sum of interior angles, there's a difference, but each interior angle, you can convert it to an exterior angle, and life is great. Life is great. I mean, life is still good with the formula, you're just gonna struggle for sure. If you're not nice with the algebra, then it's gonna suck. But if you think outside the box, then life can be good. All right, let's look at a couple of examples here. So we're solving for x. We're always solving for x, right? Some missing side, missing angle. In this case, missing angle. So we have a four-sided shape. So quadrilateral, irregular. Doesn't matter if it's regular or irregular. A four-sided shape it must add up to 360 degrees. That's non-negotiable. So if I know 3 of the 4, I can definitely figure out the fourth. So I'm going to add up 140, 70, and 110 and subtract it from 360. All right, x is going to equal 40. Five-sided shape. I know that these must add up to 540. So again, 540 minus these 4, we can figure out the fifth. So x is equal to 110. 110 degrees. Another five-sided shape. So 540 degrees, 5 sides. So 540 minus 60, 130, 130, and 120. X is equal to 100 degrees. And the last example, again, 360 degrees because it's quadrilateral, 4 sides. So 360 minus 80 minus 120 minus 100. X is equal to 60. Okay, so we want to figure out the measures of each angle in the quadrilateral. So quadrilateral is going to be 360 degrees. So that means I add all 4 of these up, and we're going to get 360. So x plus 30 plus x plus 90 plus x plus 60 plus x is equal to 360 degrees. Combine like terms. 1, 2, 3, 4 x's. So 4x plus 30, 60, 90. So 180 is equal to 360. If you subtract 180 from both sides, 4x is equal to 180. Divide both sides by 4. And x is equal to 45. All right. Plug x in to each. So we got 45, 105, 75, 135. And all these should add up to 360. Okay, so there's your basic intro into polygons. So the big takeaway is right here. This is the big takeaway. Sum of the interior, this angle. Or this formula. The measure of each angle, you just divide it by the number of sides. Sum of the exterior is always 360. And if you want each exterior, you divide 360 by n. So this is the big takeaway. We'll look at some more examples in the next video. So if you haven't done so already, please subscribe, like, comment, let me know what you think. As always, good luck, and I'll catch you in the next video.